In the theorem, if g of g is equal to 1, then for each value of g in the open disk bounded by the circle of convergence, the power series, the fact that g negative g naught to the power of n is entire when n is equal to 0, 1, 2 ensures that integral along to the contour C g of g times g negative g naught to the n dg, because this part is 0, so this part is 0. In this case, this part is 0, so we get this integral along to the contour C g negative g naught to the power of n dg is 0 because of Cauchy-Grasset theorem for every closed contour C lying in that domain. According to equation 2, this, which means this, so look at on the left hand side, integral along to the contour C s of g dg, which is this, and because of integral along to contour C g negative g naught to the n dg is equal to 0, so this part, this term is 0, so every term will be 0. Also, summation of these terms will be 0. So we get this result. Integral along to contour C s of g times dg is equal to 0 for every such contour. Then by Morera theorem in section 57, the function s of g is analytic throughout the domain because this condition holds. Here I wrote theorem 2, which is the Morera's theorem in section 57. Let f be continuous on a domain D if this condition holds for every closed contour C in D, then f is analytic throughout the domain D. So we can make a corollary for this. The sum s of g of power series is analytic at each point g interior to the circle of convergence of that series. Analytic, for the analytic, I wrote here the notion of analytic. A function f of the complex variable g is analytic at a point g naught if it has a derivative at each point in some neighborhood of g naught. Okay? The corollary is often helpful in establishing analyticity of functions and in evaluating limits. Okay, let us check some examples to understand what the theorem says. Here is the example 1. Okay. Let us show that the following function defined by means of the following equations is entire. Okay, here is the condition. F of g is when g is not equal to 0 is defined by sine g divided by g. When g is equal to 0, f of g is defined by 1. Let's consider Maclaurin series expansion of sine g, which is expressed by this here. Summation n is equal to 0 to the infinity, negative 1 to the n times g to the 2n plus 1 divided by 2n plus 1 factorial times g to the n is valid for every value of g. The series y means this series when divide each side by 1 negative 0, because for the function f of g, which is defined by this sine g divided by g. On the left hand side, you can see the exactly f of g, and on the right hand side, you can arrange some terms here. We get this. Here, it's cancelled by 1 negative g, 1 over g. Then we get this result for the sine g over g. Okay, when g is not equal to 0, this series converges to f of g. Series 5, which means this series, converges to f of g when g is equal to 0, because we just insert 0 for the variable g. Then we get 1, which is exactly the same here. Hence, representation of 5 is valid for all g. This representation valid. And f is therefore an entire function. Since sine g divided by g is equal to f of g when g is not equal to 0, and since f is continuous at g is equal to 0, we have this. Limit n goes to infinity, sine g divided by g is equal to, this is actually f of g, because f is continuous. So this is equal to f of g, f of 0, which is defined by 1. This. Actually, in fact, this is a result known beforehand, because the limit here is the definition of derivative of sine g at g is equal to 0. That is, limit n goes to infinity, sine g over g is equal to, we have add the terms sine 0 and 0 in each side, then which is exactly the form of the derivative of sine g at g is equal to 0. So we have cosine of 0, which is equal to 1. Okay.